This video is a supplement to an article I wrote with the same title, link in the description. Just read that. I'm better at writing articles than making videos. This is my DIY current voltage power monitoring thing based on an RP2040. And in this video, I want to show you how it works and how I made it. So, over here we have our instantaneous values, like whatever the voltage, current, and power is right now. And then this is a graph. It's actually sensitive enough that if I just touch it, you can see we get some voltage there, just whatever's on my body, like induced from the environment. But I have this adjustable power supply. And if I take it, and then I take one of these, which just adapts the barrel jack out into these screw terminals. And then I'll take some wire. Great, that's good. And then on this side, the left wire is our plus, which goes in the middle here. So that's... I quite like screw terminals. They're quite easy to connect and disconnect if you have the right driver, of course. You need one of these little screwdrivers for some of these smaller ones. But they're a pretty permanent feeling once you make the connection. It doesn't feel like it's gonna just disconnect randomly. So yeah, these are great. I support screw terminals. Plug this in. If I turn it on, you'll see, oh, there's our voltage. And you can see on that graph there, we get voltage over time. So if I tweak this, you can see we're getting that change of voltage on the screen there. So if all you wanted was a voltmeter, this is like a graphical two-dimensional voltmeter that also gives you data over time. But if we have a load like this, which is a little tiny incandescent light bulb, it's so cute, look. You can almost forgive it for using 10 times more power than an LED. And then I have this, it's just some copper tape adhered to this cardboard, which I have a hole cut into, so if we plug in our bulb, we get the contacts broken out onto these two strips. Hook up some alligator clips. Polarity doesn't matter because it's a resistor, basically. It doesn't matter which way it goes. The wiring can get a little tricky here. I'm actually gonna turn this off for a second. So you want the negative line of the power supply to go to V and minus, which is how we had it before. The positive side goes to V bus, and so does the positive side of the load. In this case, it doesn't really matter what side it is, but what that means is both this wire and the red wire will go into this middle connector. It's a little tricky, hold on. And then screw that one down. And then the negative side goes to the V in plus. I think it's a little confusing because I think, yeah, V in plus and V in minus are common. So you have to be really careful because if you attach the power supply to V in plus and V in minus, it will short through the shunt and then that will not be what you want. So now, if I turn this on, hold my light bulb carefully, and then turn this up. Ah, beautiful, and it glows. And, ouch, hot. And you can see, not only do we have voltage, but we have current and power now. So I can actually press B, C. I can change the graph between voltage, current, and power. In this case, it's not going to be so interesting because this is a resistive load. The current is right in step with the voltage, but you can see it change. And if I press B, I can change the length of time displayed all the way up to 20 seconds. Or if I go as short as half a second, you can see the very immediate results of my voltage change. So it's pretty quick to update. And the A button pauses everything. So if I switch to, let's pick a longer time frame, and then let's say I've captured something really interesting, like some fluctuation, and then I hit A, then I pause it, and then it doesn't matter what I do, the values don't change until I press A again, then everything updates accordingly. So yeah, I didn't do a great job connecting it, clearly. Oh, there we go. So this chip here should be able to do up to 85 volts at 10 amps, 85 volts DC, that is. I haven't tested it that high, but it should work up to that. I've tried mostly like 12 and maybe even 24 volts, but I haven't gone up to 85. But it will work with a lot smaller currents and voltages. So let me demonstrate that. We'll get rid of this. So this is a coin cell battery. It's about 3 volts nominally. And if I unpause this and turn this switch on, you should be able to see, we see about 3 volts on that. So if I take that and then screw that down, and then we take an LED, I wonder what color this one's gonna be. It's a surprise. We don't know. And then we plug that in here, this way. Yeah, there we go. And it's blue. Here, let's screw that down. And there's our blue LED, and we can see the voltage drop a little bit. And if I change it to milliamps, you can see the current draw there. It looks like it's going down slowly over time. Maybe the battery voltage is falling. And if I turn on and off, oh, that's better. If I turn on and off our battery, you'll see the LED go on and off. So yeah, it's auto ranging, and it works at small voltages and currents, which is great. The y-axis extents are based on a log base 2 scale, so it'll go, you know, an eighth of a volt, a fourth of a volt, half a volt, 2 volts, as the extents of the y-axis, as your data changes. And before I show you how I made it, let me just replace this LED with a funner LED. No, that was not right. There we go. This is one of those LEDs that is like magical because it has some sort of like blinking circuit inside of itself that's just so tiny. And you can see this thing takes measurements frequently enough that you can actually see the waveform of the blinking LED on the screen. So if I tweak this to half a second, you can see in current the blinking of the LED and even the fade out. So you can see the fade, and then when it blinks, you see the peak. And you can imagine that in reality, it's gonna be probably more of a square wave. So it's not like oscilloscope level voltage over time, but it's pretty frequent. Okay, enough of this. Okay, so first I was running this with the battery, but of course you don't have to. You can always just plug it in and, oops, that'll work just as well. Although the battery does help a lot, I think, because I found like weird ground loop stuff or some sort of like parasitic current stuff happens when you use a USB connection to power it that is powered by something that's connected to your wall, like a USB adapter or a laptop that's charging or whatever, with a voltage source like this that is also powered from the wall. Like if I measure this thing with this thing while this is connected to a desktop computer that's powered by the wall, I'll see like 30 or 40 volts just like randomly through this. So I think there's some sort of weird bad isolation thing going on, which is kind of scary. Maybe that's just this thing's fault. But the battery helps with that. So probably a good idea, but we don't need it. Of course, this is just 3 AAAs. So it starts with this Feather RP2040. You could use a Pico or whatever if you want instead, but this is just very convenient because it has the easy I2C connector and the compatible set of wings, they call them, which are like Pi hats. There's not too much to say about this, except these are the sockets I soldered onto this thing, and you might notice that they're a lot shorter than the 0.1 inch sockets you might install for something like this. They actually sell these short sockets, and of course they sell short pin headers. And these are great because they're a much lower profile connection. That's just an aesthetic thing, I guess, but. And then this is the Featherwing OLED. It's really a very beautiful display. It's great too because it's really easy because it's I2C. And the best part is that it comes with these ABC buttons, so no extra work to attach buttons to this. This is all the input this device needs, and the reset button, of course. And then we just have this 4-pin cable which connects to this thing. And this is just a breakout board for the INA228 power monitor chip from TI. And it's great because it breaks up the chip and gives you that shunt resistor and the easy screw terminals. So it does everything for you. And the whole thing is mounted on this swirly grid, they call it. Basically aluminum PCB material with these M2.5 holes drilled in it. And then I use these nylon M2.5 screws to secure the boards to it. I don't really like these screws, so if you can find metal M2.5 hardware, I would just use that. If anyone's making this, probably no one's making this. And then there's the feet. That's the last thing. It has feet, which, you know, that's important. People forget the feet, but the feet, you need these feet or else it slides all around. This is really, it stays where you put it. Let me plug this back in now. The software for this thing is written in CircuitPython. I did have to overclock the RP2040 up to 300 megahertz to get this to work at what I thought was a good speed, which is technically out of spec. So warning if you care about like a warranty or something that might matter or some sort of like problem that might occur there. This board runs great at that speed. I've had no problems with it, no stability issues, and I think the RP2040s are like really overclockable. So I'm not worried about it, but be aware of that. I have all the software and stuff online if you want to download it and take a look at it. It's not too complicated. I use this great library called CircuitPython uplot, which is a port of uplot to CircuitPython, which creates this great plot here, which renders pretty well on this 1-bit screen. Although, maybe you can find a place in the code to optimize it further because, again, I just resorted to overclocking it. So there's probably ways to make this run better that I haven't figured out yet. I think the I2C bus is a real bottleneck because it runs at 400 kilohertz and it has to update both the display and the current sensor. So if you can find a way to maybe do something else to speed that up, I don't know. Put this in a different I2C bus if you can no, you need to do something else in the hardware to split those things up. So I just sort of gave up there. And there's one other interesting thing about the software. So if I go into the code and I'm actually gonna plug this into my computer really quick. So what I just did was I turned off the calibration for this thing's voltage. And now I'm gonna reconnect that adjustable power supply to this thing. So you'll notice the voltage here doesn't look quite like the voltage here. If I bring it all the way up to 12.2, you'll see that it looks more like 11.7, not exactly right. And it's not just the voltmeter on this thing being kind of shoddy. If I get a third-party source, this multimeter, and I check, you can see, oops, we're seeing 12.2 volts here, and this thing is seeing 11.65. So you can see as I tweak this, the voltage is a little off. So you can see we have 7.14, at 3.534, it looks more like 3.0. So what I did was I moved this thing around. I went up and down the voltage range, and then I took all the data and put it in a table where X is the value here and Y is the actual value as measured by the multimeter. And then I did a linear regression. I did this all in Desmos, which was just very easy. And then I took that and put that in the calibrate function in Python. And then once you do that, the values become very accurate. Here, let me actually put calibration back on, and then we can run it. So now that calibration is back on, you can see already that the values look way closer, and they look a lot closer to the multimeter values as well. So if I bring this all the way up to 12, yep, 12.20, 12.22, pretty close, 9.21, 9.22. So basically, it's much closer now. I didn't calibrate the current values because I don't really have the equipment to do that. I would need another current voltage power device, and I built this because I needed one of those, so I don't really have anything to test that. I guess you could use a resistor with a known value and then see what voltage falls across it, and then Ohm's law. I don't know. I could think about that. There is one problem with the calibration. The values are really accurate, but it messes up the zero, because this thing never returns a value less than 0 volts. It'll never say, oh, there's negative 0.5 volts on the bus. But the problem is, once you apply calibration, X of 0 becomes like Y equals 0.5. So you would never get a 0 on this. The lowest voltage it would show was like 0.5 after applying calibration. But I didn't want it to show 0.5 volts when there was nothing on it. So I just took everything less than like 0.1 and brought it all down to 0 volts, and then everything greater than 0.1, I did run calibration on it. So it's a little discontinuous, and the consequence, I think, is that you really practically can't measure anything less than 0.5 volts on this, but I wasn't going to do that anyways, so whatever. So that's all I have. Check out the article if you want more information, and yeah, thank you very much for watching. Like, subscribe. I'm supposed to say that, right? You have to like and subscribe.